finally we get to move on to our discussion of Lewis dot structures and start putting together and drawing some pictures of covalent compounds. Very exciting. So these pictures, known as Lewis dot structures, are going to follow what's known as the octet rule. And so on the handout there, I have a picture of Tony the Tiger. You can imagine him saying 8 is great. And so all atoms want to be surrounded by 8 electrons. 8 is the magic number here. They want that full valence shell. There's 2 big exceptions. So in the first row of the periodic table, we have hydrogen and helium. They're so tiny. They really are very tiny, and they only have 1 shell. So they're satisfied with 2 electrons. And let's go over some of the symbols as well. So earlier we were working on dots diagrams. And so that 1 dot, when you draw it, stands for just 1 electron. Next, you can draw 2 dots, and this is more common actually. 2 dots side by side. That's called a lone pair. And this lone pair represents 2 unshared electrons, and it's not involved in any kind of bond. When you have what's known as a bond, you're going to draw that as a single line, just like that, and that's called a bond or a bonded pair. And it represents 2 shared electrons. Where does that come from? Well, you can imagine 2 electrons, but they're being shared, so we want to connect them. So that's where the idea of the bond being represented by a line comes from. This specifically is a single bond, and it's just 2 electrons. And we can do a double bond, which has 2 lines, so that represents 4 electrons. Each line counts for 2. And the last one you'll see is known as a triple bond. So 3 lines. Each line counts for 2 electrons. So if you see a triple bond, it represents a total of 6 electrons. Alrighty, so let's learn how to draw the Lewis dot structure for carbon tetraiodide. The first thing that we're going to tackle is what I like to call the electron map. So this tells us how many electrons we have available for our picture. We can only use that amount. We can't use more and you can't use less. It's going to be based on the number of valence electrons. So for carbon, since carbon's in group 4, I'm going to do 4 electrons. And then we have iodide or iodine. And there's 4 of them. Iodine is in group 7, so I'll do 7 electrons, but since there's 4, I need to multiply by 4. So 28 plus 4, this structure should have exactly 32 electrons. It can't use more, it can't use less. So next we need to think about how are things going to be connected in the structure. The rule of thumb is that you want to put the atom that's best at sharing, so the one that's least electronegative, in the middle. Carbon is a great candidate. Carbon is to the left of the iodide, which means it's going to be less electronegative as well. So carbon goes in the middle, and I'm going to connect the 4 iodine atoms to that central carbon. At this point, I have what's known as a skeletal structure. And you always want to check 2 things after you put together your structure. One, you want to check that every single atom has 8 around it. So for instance, and you might have to cover up the rest of it. If we look at this iodine, right now it just has 1 line, which represents 2 electrons. So this iodine on top is only feeling 2 electrons. So I'm going to put some lone pairs, put 6 electrons. So now we got 2, 4, 6, 8 around the iodine. I'm going to do something similar over here. It's just feeling 2 currently. So 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. So now all the iodine, we went through and checked them all. They all have 8 electrons. We've satisfied the octet rule. Looking at carbon, carbon has these 4 bonds, 1, 2, 3, 4, connected to it. So since it has 4 bonds and each bond is worth 2 electrons, 4 times 2, we have 8. 2, 4, 6, 8. So we've satisfied the octet rule on the carbon as well. Once you check your octets, so we're like, yes, everybody's got 8. The second thing that you're going to want to check is that you've only used 32. That's all you can spend, and you can't use less. We can't use like 30. We got to use exactly 32. So I just go through real quick. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. And I'm like happy about that I accomplished my 2 goals. I satisfied all the octets, and I used the appropriate number of electrons, and that means I have a correct structure. Let's put together some more Lewis dot structures. So here we have PH3. Phosphorus is in group 5. So we have 5 valence electrons. We have 3 hydrogens. Hydrogens in group 1. So I'm going to do 1 electron times 3, since there's 3 of them. And that gives us a total of 8 electrons to work with. Now I know I said to use the least electronegative as your central atom, but there's exceptions to everything in this section. And one of the main things is that hydrogen can never ever be a central atom. Hydrogen only likes to have 2 electrons. So what hydrogen will do is just 1 single bond. That's your only option for hydrogen. You can never do anything else. So we should never see like hydrogen with a bond and with some electrons. That would be super, super wrong. So the only thing hydrogen does is just 1 single bond. That won't make a very good central atom. So we're going to have to put phosphorus in the middle. And we're going to connect the 3 hydrogen to that. It doesn't matter, like, kind of like with Lewis dot diagrams, we can put the hydrogens wherever we want. We just need 3 of them. Hydrogen just wants that 1 bond, so all the hydrogens are good to go. Phosphorus, however, does need to obey the octet rule. So right now it has 2, 4, 6, and we need to get it up to 8. So I'll put 2 dots, so it has 8 electrons. 2, 4, 6, 8, that also corresponds to the total number. So we're done with this structure. It looks good. We've checked both the octets and our electron math. All right, so sulfur's in group 6, so it donates 6 electrons. We have 2 chlorines, group 7, but I'm going to multiply it by 2. So I have a total of 20 electrons that I need to use when I build this structure. Looking at the periodic table, sulfur is less electronegative than chlorine. So sulfur, because it's less electronegative, is going to be my central atom. I'm going to attach both chlorines. Personally, I like to take care of the octets first. So right now I'm noticing that chlorine only has 2 electrons or 1 bond. So I'm going to do 2, 4, 6, 8. Same thing on this side. 1, 2, 3, 4, 5, 6, 7, 8. Both chlorines now have 8. I look at sulfur, it's got 2 and 4. So it needs 4 more electrons. So now everybody has 8 electrons. All the octets are satisfied. Next, I need to check my electron math. I had 20. Did I use 20? So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So I had 20, I used 20, I'm good to go. Continuing with our practice, we're asked to draw Lewis-Dot structure of hydrochloric acid. Always start with the math. Hydrogen's in group 1, so we have 1 electron. Chlorine's in group 7, 7 electrons. Total of 8 valence electrons. There's just 2 atoms here, so we don't have to worry about a central atom, right? Central means to be in the middle, but when you only have 2, nobody's in the middle. Hydrogen just wants to have that 1 bond, so the hydrogen's good. Chlorine, however, needs 8. Right now it has 2. So I'm going to do 3, 4, 5, 6, 7, 8. So now the octet 2, 4, 6, 8 is satisfied on chlorine, and I've also used the correct number of electrons. Let's move on. So carbon is in group 4. I have 3 hydrogens. So I'm going to do 1 electron, since they're in group 1, times 3. And then we have fluorine, which is in group 7. So 4 plus 3 plus 7, that gives us 14 electrons altogether. When thinking about our central atom here, hydrogen can never be a central atom because it only does 1 bond. And fluorine is the most electronegative, the biggest hog, the biggest bully. We're not putting fluorine in the middle. So carbon is our best candidate for our central atom. So I'm going to put carbon in the middle, and I'm going to attach everybody to carbon. It doesn't matter where you put your fluorine. I mean, you could put the 3 hydrogens, the fluorine down there. That part isn't important. Octets. So hydrogen is good to go because hydrogen just wants 1 bond. Fluorine has 2, so I'll do 3, 4, 5, 6, 7, 8. Hydrogen, hydrogen, and then let's look at carbon. So carbon has 2, 4, 6, 8. So carbon's good to go. Don't forget always to do a total count. Make sure you use the right number all together, so 14. So 2, 4, 6, 8, 10, 12, 14. And we're good to go on that structure. Let's draw the Lewis-Dot structure for water. So we have 2 hydrogens. So 1 electron times 2. We have 1 oxygen, that's in group 6. So it has 6 valence electrons for a total of 8 valence electrons. Oxygen has to serve as our central atom because hydrogen is never a central atom. Right now the oxygen has 4 electrons or 2 bonds around it. So I'm going to add 4 more to get it up to 8. So we're looking at 2, 4, 6, 8. And it also used 8 in total, so that's good to go. This one is a little bit different. You might be wondering, why did they break it down like this? Why did they write CH3OH instead of writing CH4O? Well, they're actually doing us a favor writing it like this. This tells us how the atoms are connected. So we have carbon connected to 3 hydrogens. And then we have an oxygen connected to that. And this last hydrogen is just connected to that oxygen. So that was really useful. It told us how everything was connected. We still have to do our electron math. So we have a carbon with 4 hydrogens altogether, so another 4 electrons. And then that oxygen, which is group 6, 6 electrons. So 14 electrons. Carbon is good to go with its octet. 2, 4, 6, 8. There's 4 bonds coming into carbon, which means it has the 8 electrons that it needs. Right now, oxygen only has 2 bonds, or 4 electrons. So I'll do 2 more. So we're looking at 2, 4, 6, 8 around the oxygen. And then, and then we got to check the total. So we need to check that we used exactly 14. 2, 4, 6, 8, 10, 12, 14. And we're good on both our octets and our electron math. Alrighty, let's finish up with these last two examples of structures that only have single bonds. So here we have carbon, so I'll do 4 electrons for that, 2 hydrogens, each donating 1 electron, so 2 electrons from that, and then 2 chlorines. Chlorines in group 7, but it comes out twice, so 14 electrons. So altogether, this looks like we have 20 electrons for this structure. Carbon is our best candidate for a central atom here because it's the least electronegative and it's not hydrogen. So by connecting the 4 other atoms to carbon, I've satisfied carbon's octet, 2, 4, 6, 8. Hydrogens are good to go with just a single bond. Chlorine right now only has 2, so I'm going to have to put 6 single electrons or 3 lone pairs around chlorine. So 2, 4, 6, 8. Same thing with this chlorine up here. So 2, 4, 6, 8. And now that the octets are good, I need to make sure I only use 20. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So perfect, and we're done. Let's start with the electron math over here. Although this is also, like in a previous example, written kind of separate. And this is the second time we've seen the OH ending. So you might start wondering, well, what does that mean? Why do we keep on seeing OH? OH is associated with alcohol. And there's so many different types of alcohols. So I know when we think of alcohol, we think of drinking alcohol. Oddly enough, this is drinking alcohol. So this structure is for ethanol specifically. The OL on a name also references the alcohol. So if you see a compound, octanol, propanol, methanol, if you hear that OL ending, that means it has an alcohol group or an OH group on its Lewis-Dot structure. Just for your own knowledge, I never ask any students that at this point. That's organic chemistry if it's interesting to you. Let's learn how to draw this though. We have 2 carbons. So 2 times the 4 electrons. So 8 electrons there. 5 hydrogens. That's another 5 electrons. 1 oxygen. 6 electrons. And that last hydrogen, so 1 more electron. So 6, 12, it looks like we have 20 electrons all together. Who's going to be our central atom? Well, this is going to be a bigger molecule. We're getting into larger molecules here. So we're actually going to have more than 1 central atom. So we have carbon, and we have a second carbon. And then we have our oxygen, which we know we have the OH on the end. That last hydrogen needs to be connected to our oxygen. But how do we interpret this part? Well, we've been talking how we need 8 electrons on carbon, but we can't put more than 8 electrons. So I can't come here and put 1, 2, 3, 4, 5. That's just not allowed. This is that's super, super bad, because that would mean carbon had 2, 4, 6, 8. I lost track. 2, 4, 6, 8, 10, 12. 12 electrons around it, and it can only have 8. It can't have more than 8. It can't have less than 8. So let's erase this, because that's a disaster. So we need to be able to distribute these 5 electrons so that the 2 carbons, and we know they belong to the carbon because of the way this is written, only have 8 electrons each. So if I put 3 hydrogens here, that's not any kind of violation. That's perfect. 2, 4, 6, 8. And then I could put 2 here. Not 2, 4, 6, 8. So that's good as well. And then that's all 5. 1, 2, 3, 4, 5. We have our oxygen, which only has 4. So I'll put 2 more electrons, 2 lone pairs, 4 electrons on the oxygen. And hydrogen is good on the end there. So all the octets are good now. Let's check the 20. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So we're good on both the octets and the electron map. It just takes a little bit longer with the larger molecules. And you might have to try it one way. Do it in pencil. You might have to try it one way in a race because you're like, oh, I can't connect it that way. I won't have enough electrons to get the octets good. Or that's going to give me more than 8 electrons on anything, on carbon, on something like that, and that's not allowed either. So be patient and be ready to erase quite a bit and try again.